Recording in progress.
All right. Good morning, everyone, and welcome back after our 1 week hiatus. And let's maybe get back where we left off last time. We've briefly discussed, reiterated the classic Diffie-Hellman key exchange and the fact that it is, in fact, a so-called non-interactive key exchange in the sense that the two parties, Alice and Bob, can just simultaneously exchange their messages, right? It's not like Bob has to wait for, excuse me, Bob has to wait for Alice to first send her message before he sends his message, right? So the two messages don't depend on one another. We just exchange these messages, and then every one of them, both Alice and Bob, can just derive this joint key g to the a times b. And this is even possible if Alice and Bob have, say, never met before, right? We could say they can just somehow non-interactively agree on a generator G by just hashing their two identities. That would be with a random oracle, right? Typically, we would model that with a random oracle, but in the real world, we would just use SHA-2 or something similar for that. Good. So the upshot is Alice does not need to wait for Bob to send his message in order to send hers. Then we went to this question of three-party key exchange. Right? What if we have Alice, Bob, and Charlie, right? If there's not just two of those who want to agree on a key, like if we think about this as a graph, right? So two-party non-interactive key exchange allows us to just ad hoc establish a key between every edge in a graph, right? But the generalization now, three-party key exchange, would be an ad hoc mechanism to generate keys for every triangle in a graph, right? Alice, Bob, Charlie, we want them to generate a key or generate a key that's unique to such a triangle. And we thought a little bit about this. The proper way to do this, to define such a key, would be G to the ABC, right? So other attempts like, let's say, take any degree 2 polynomial, G to the A plus B plus C, something like this. This is not secure. Someone who watches just the information that goes over the channel. Let's write this down maybe. If we set the key was G to the A plus B plus C, right, then someone who just observes what goes over the channel could compute this, right? See, this is bad, right? Because, I mean, what we want of a key exchange is that the parties involved in it can derive this key, but any outside observer who just sees what messages they're sending to one another should not be able to recover such a key. Let's take that off again. Good. And it turns out standard cryptographic groups are not enough for this. Right? So there's even so-called black box separations, which means that if you just use the group as a group, right? If you don't use any other properties, right? Recall typical candidates, typical candidate for our group G is like G equals the quadratic residues of in some FP star, right? That means all squares of elements of multiplicative elements in a prime field. This is, let's say, the classic standard candidate for, I mean, I see a few confused faces, so let's just write that down. That's all the x squares for x element fp star, right? This is a group, multiplicative group, and if let's say P is 2Q plus 1, then this is even a prime order group. Good. This is our standard candidate, right? So maybe if you use some specific properties about this candidate, you can build a non-interactive key exchange. But if you just use the group generically, just as a group, right? Just as we typically do, that you just multiply and exponentiate group elements, but don't use any other properties of the group, we know that this is impossible. They're so-called black box impossibilities, which show that from a so-called generic group, and a generic group means you're really just using the group law and not any specifics about this group, right? A group can have much more additional structure attached to it. For instance, here, this is a multiplicative group in a finite field. Being in a finite field, or surrounded by a finite field, that's already additional structure, right? So maybe something is possible there, but just using the group laws is not enough, right? We do have black box impossibilities in the so-called generic group model, where honest parties and the adversary can only sort of access the group by legitimate group operations. This is an idealized model, right? So it doesn't capture really what's happening in the real world, but just says you have to do something more clever than just multiplying together group elements if you were ever to succeed to build a three-party non-interactive key exchange from an arbitrary group. This was a lot of context information. So, by the way, this we don't need. Good. Let's go on. And what the new idea that enabled this concept of three-party key exchange to be realized is an object called bilinear maps or bilinear groups. So we say that a group G is of order n, right? And n is typically prime, but we'll also see a setting where n is not prime, where n is the product of two primes, right? That's nothing too surprising in cryptography. But we say that a group G is a bilinear group if there exists a group GT, which is isomorphic to G, right? There is some isomorphism between these two, but their representations are not the same. And we have a map. We call it typically E. That's typically called a bilinear pairing, such that it holds for all G and H in this group G that E G comma H is E H comma G. So this is called symmetry, right? The pairing is symmetric. And second, we ask for linearity in here in the first argument. It holds that if we sort of fix an f, right, then this function E is a group homomorphism in the first argument, right? E of G times H comma F is the same as E of G comma F times E of H comma F. And of course, since we're having this first property, symmetry, this must also hold for the second argument. That's why they're called bilinear, right? We're not just linear in the first argument, we're also linear or a group homomorphism in the second argument. But then, of course, this also means that, let's say, e of g to the a times h to the b comma f. That's why we call this bilinear. And but every group homomorphism has this property: is e comma g of f to the a times e of h comma f to the b, right? This follows from this linearity property, this group homomorphism property. And finally, we have a non-triviality requirement, right, which says that if G is a generator of the so-called source group, right, this G, we call that the, we call that the source group. And this guy here, we call it the target group. Now you know why there's a T, why there's a GT, that's the target group. So if G is a generator of the source group, then EGG is a generator of the target group. So, and lastly, we require this function E to be efficiently computable. What if we drop that last requirement? How could we build bilinear groups if we didn't have this requirement that E is efficiently computable? That just such a map exists. I claim if we don't require that E to be efficiently computable, then every group is a bilinear group. How would we do that? Let's take any cyclic group G. How can we make it bilinear? I think we should have a coffee dispenser here for people to wake up in the morning. I could have a second coffee. How would we do it? So why are bilinear maps not something magic without this last requirement? Which is? So what do we compute? I mean, obviously we have to do something not efficiently computable, right? What would that be? What would be the no, but what is GT, right? I'm just giving you a group G. What is GT? Okay, proposal GT is the same as G. Yeah. How? So I think the next slide. Oh no, we have space on the next slide. So let's call that an inefficient pairing. Let's say E of G to the X, comma, G to the Y, right? We're having a cyclic group. We can express everything in terms of generator G. What would we do? So if your candidate is E of, E, something like G to the X plus Y, I claim this is not bilinear. So in particular, when you're having let's try it, right? When we're replacing a G to the X by G to the X times G to the Z, right? Let's look at that. E of comma G to the Y, according to you, this would be G to the X plus Z plus Y, right? And this is now something like G to the X plus Y times G to the Z. And this is your E of, G to the X, comma, G to the Y times G to the Z, right? There's some G to the Y missing here. So what do we do instead? Again, it doesn't have to be efficiently computable. What would we do? Any proposals? A bit more specific. So what inefficient? In the end, a bilinear pairing, we want to compute a product in the exponent, right? So if we go back here, right, and use just both properties, e of g to the x, comma g to the y, this should be e g to the x times y. Right? This follows immediately from the linearity and symmetry property, right? So y is e of g to the x comma f, the same as e of, well, this is, right, e to the g and so forth times g, this whole x times, right? Whoops. X times, comma, f is e of g, comma, f, and so forth, e of g, comma, f, again, x times, which is e of g, f to the x, right? So we get that e of g to the x, g to the y is egg of x times y. So what would be any proposal? Yeah, exactly. So this does not work. So what we do instead is we would compute it like this, e of g to the x, g to the y. First, compute the discrete logarithm of g to the x, let's say with the basis x, which is just x, and d log g to the y, which is y, and then compute g to the x times y, right? So if we can brute force discrete logarithms, then we can easily define such a bilinear pairing. Now, good. In groups without pairings, or that don't come with a pairing, we can do that with a discrete logarithm. But now the magic of an actual bilinear pairing is that we can do this without magic, without computing discrete logarithms, right? We can compute something of the form, give me g to the x, g to the y, and then some other generated to the x times y without doing any actual magic, any actual intractable computation. Good. Okay. So here, this may be as an exercise. I mean, this I just did. Yeah, no, don't need an exercise for this. So it follows immediately that g to the e of g to the a comma g to the b is g to the a times b. And e of 1 comma h is just 1 in the target group, right? You can think of, I mean, 1 is g to the 0. That immediately follows from this first property. 0 times anything else is, by the way, it should be gt, generator of the target group, AB. And good. Such bilinear maps are called type 1 bilinear maps. There's others. This is symmetric bilinear map. So here we're pairing up the group G with itself. But there's other pairings where you're having, let's say, a left group and a right group. They are isomorphic, but you're having two different source groups, right? But those are mostly considered for purposes of efficiency, right? Computing an asymmetric bilinear groups is potentially or typically more efficient than computing in a symmetric bilinear group. Also, there's some hardness assumptions, which we're not going to go into, which make sense to define in asymmetric bilinear groups, but not in symmetric ones. Good. And really, in literature, we, until, let's say, a few years ago, only had two examples. They're pretty much the same, namely elliptic groups or with elliptic curve groups with the Weyl pairing and with the Tate pairing, right? There's so two, let's say, rational maps that can be computed on these algebraic curves that give us such a pairing operation, right? I mean, again, I considered doing a little bit of background on this type of algebraic geometry in this course, but since I think we had a few missed lectures and or whatnot, this I'll spare you this excursion, right? Because this sort of also wanders a bit off from the other material that I'm doing in this course. But like the name elliptic curve is not new to you. You've heard that sort of mathematicians like to study these curves that are typically given. I mean, this is obviously an elliptic curve over the reals or over a field of characteristic 0, whereas in crypto we look at these in finite fields or fields of finite prime characteristic and not characteristic 0. I mean, you might know the special property that these curves have, right? That you can define a group law. You're having 2 points, right? And you can define a group law by putting a line through these 2 points, right? In such an elliptic curve, it's a degree 3 curve. There's always going to be a unique third point where this line crosses this curve. And then the group, we can define a group law just by mirroring this point, and somehow magically, right, that this sort of commutes is not the magic. The magic is that this associates, right? That this group law obeys associativity. That's sort of the, let's say, the step that requires a bit of work and insight. But these curves, or these groups defined on these curves, kind of have enough algebraic structure to define such a pairing or such a bilinear pairing on them. Right? And but what really matters for us is that essentially groups allow us for addition in the exponent and multiplication with values that we know in ZP, right? But what pairings do, they give us one multiplication, right? So in typically, again, this is the hard problem in this is the DDH problem. Given g to the x and g to the y, computing g to the xy is hard. That's a computational Diffie-Hellman problem. And in fact, we make the decisional Diffie-Hellman problem that says, given those two guys, distinguishing this one here from uniform is hard, right? So, but elliptic curves or pairing groups allow us to kind of cheat this, right? So that's maybe one of the first things in a group where we have in a symmetric pairing or a symmetric pairing group, the way we've just introduced it, we cannot make the DDH assumption, right? Because something like this, g to the xy, is trivially distinguishable from something uniform. How would we do this? Let's say we have a group G, we have a pairing defined on this group. Now, let's say we're gonna get a tuple g, comma g to the x, g to the y, g to the xy. How are we gonna distinguish the last one from uniform? How are we gonna do this? If we have a pairing, you're getting these four values. Any suggestion? I see discussions. What could we do? Yes. Yes, and you're saying, so you said we compute e of g to the x, comma g to the y. We know this is crap. This is e of g to the xy. What's the other value we compute? Exactly. Which is also e g to the xy, right? So if someone gives us a Diffie-Hellman quadruple, and those two values here are always the same. Whereas if we replace this guy here with uniform, then we get a random value. So that's one thing to keep in mind. In these bilinear groups, we cannot make the Diffie-Hellman assumption. DDH assumption false in bilinear groups G. Okay, but now we're gonna go to the reason why they were originally introduced, which is three-party key exchange, right? We're going to look at this famous paper from 2001, which opened an entire area of cryptography, right? There's literally thousands of papers that build on this very simple idea of three-party key exchange. And how are we going to do this? Well, we're going to say let G be a linear group of prime order P, and E G to G to GT, a bilinear pairing. Pairing. So again, we have Alice, Bob, and Charlie, right? So what does Alice do? She chooses a uniformly random A from ZP, Bob chooses a uniformly random B from ZP, and Charlie a uniformly random Z from ZP. Then Alice just sends one message to each of them. In fact, it's the same message. She just sends G to the A to, you know what, let's use different colors for these three. Alice. It's visible, it is Bob. So Bob and Charlie. So Charlie sends G to the C to both Bob and Alice. And Bob, of course, sends G to the B to both Alice and Charlie, right? And now this joint key that we derive, let's maybe try this color, see if we can see this. So Bob computes a key KB, which is just E of G to the A, comma, G to the C to the B. Alice computes a key KA, which is, she takes the messages of Bob, which is G to the B, and of Charlie, G to the C, and raises it to A. And Charlie takes G to the, now let's make first G to the A, G to the A, and G to the B, and raises it to C, right? And what holds for these keys? They're all the same. Exactly. So of course it holds, this thing is E, G, G of A, B, C. And also here, this is E, G, G of A, B, C. This E, G, G of A, B, C. Great. So we have derived the key. We see correctness of this protocol, right? And how can we now argue security of this protocol? So correctness, again, follows easily from the algebraic properties of this bilinear pairing. But how can we now reason security of this protocol? The first question we should ask ourselves would be, what assumption do we base this on, right? So what assumption would we base security on? Any suggestions? Yes. No, the function E is public. The function E is sort of, no, let's assume that's public. That's part of your implementation of your of the code of your three-party key exchange. So E, sort of hiding E would feel like security by obscurity, and it would basically mean they already have a shared secret, right? So if E was hard to find, then A, B, and C already have a secret, then what do we need key exchange for? Then just expand it via a pseudo-random function. So A, B, and C, at the get-go, they don't share any secret, right? They don't have any joint secret. Good. So it seems kind of weird, right? We've seen the DDH assumption, but a moment ago, I've told you the DDH assumption cannot hold, and the DDH assumption is essentially everything we've seen so far in this lecture, right? And I just told you, in such a group, the DDH assumption cannot hold. Let's go a step back. Let me ask you, what is the DDH assumption and where does it come from? So what does the DDH assumption say, right? Basically, now let's use blue again. DDH says G to the A, G to the B, or G, comma, G to the AB is computationally indistinguishable from G, G to the A, G to the B, and let's say G to the U. Uniformly random G. Why, right? Where did this assumption come from? Why did people start? It's an extremely useful assumption, right? We see that Kramer-Shoup encryption is one thing we got from it, but why did people start making this assumption? Yes. I mean, if discrete logarithm in such a group is false, then we cannot make this assumption, right? Because then given G to the A and G to the B, you can just compute A and B and compute G to the AB. So if D log is false, this assumption is false. This is a stronger assumption than the discrete logarithm assumption. Right? So, but why did people start making this assumption? Typically, when I do the undergrad cryptography course. This is sort of the first thing I tell people to remember about the DDH assumption. Right. So any suggestions or where this assumption, or any guesses where this assumption came from? Go ahead. Precisely. G to the A, G to the B. This is exactly what the adversary sees in a Diffie-Hellman key exchange. He knows the generator G. He knows G to the A, that's a public message. He sees G to the B. And now his goal is to distinguish actual key, G to the AB, from a fresh uniform key, right? This is precisely the security of Diffie-Hellman key exchange made as an assumption. So the Diffie-Hellman key exchange, the decisional Diffie-Hellman assumption is just saying that we assume that keys produced by the basic Diffie-Hellman key exchange protocol look uniform to someone who just sees G to the A and G to the B. That's precisely what the DDH assumption is. It's assuming security of this protocol. Good. And really think of it, the only thing that differs here is G to the AB versus G to the U, right? So a real key versus a fake or uniformly random chosen key given the protocol transcript, right? This is the key. Random key, the key, and this is the protocol transcript. Protocol transcript. Great. Okay, so what do you think? How are we going to argue security of this protocol? We just assume it's secure, right? We phrase, really what we're doing now is we're phrasing security of this protocol as an assumption. So how can we establish security? Well, we will make a new assumption. And we call this the bilinear decisional Diffie-Hellman assumption, or for short, BDH. Let's use blue again. BDH. Right? We say G is a generator of a group G. A, B, C, and this value Z are chosen uniformly random. The assumption states that G to the A, G to the B, G to the C, and G to the A, G to the B, G to the C versus so here on the one hand side, we have EGG to the ABC. And on the other side, we have EGG to the Z. Now, obviously, since Z is chosen uniformly random, EGG to the Z is a uniformly random key, group element independent of the rest. Right? So this is a uniformly random key. Right? That's sort of how we then use this. But again, this is the real key. And this is a uniform key. And again, this stuff here, this is just a protocol transcript. Transcript and protocol transcript. Of course, as I just said, this assumption is directly equivalent to the semi-honest security of the passive security of the three-party Diffie-Hellman protocol that we've just seen. Semi-honest security or passive security. If we have an active adversary who can sort of substitute let's say messages sent by the honest parties, right? Then this is not enough, right? Then we have man-in-the-middle attacks, then we need to protect ourselves with authentication. Right? I hope I'm not saying something entirely new here. But are there any questions? Yes. CDH. A CDH version of this, we can use it, but then what kind of good? Let's say we want to. How would the CDH version of this problem look like? CDH. Mm-hmm. Because the CDH. Yes. CDH, that is correct. So in a bilinear group, we've just seen that the DDH assumption is false, but CDH should still hold, right? So if CDH doesn't hold, we do have a problem, right? If CDH if CDH doesn't hold, that's a very good point. So if in our source group, if CDH doesn't hold, then this assumption doesn't hold. But what we would actually need is the reverse, right? If we wanted to argue security on CDH, we would need that if CDH holds, then this assumption holds. That's what we would need to argue security of this protocol from CDH. But what we have is the exact opposite, right? So if CDH is false, then this assumption is false. Or stating it trivially, if this assumption is true, then CDH must also be true in the source group, which doesn't tell us anything about this assumption, right? We want to not, let's say, derive hardness of other assumptions from this assumption. We would like to base this assumption on other assumptions. But this is a good point, right? It's just that the arrow goes in the wrong direction. Does this make sense? You know what? Let's put this on exercise sheet. Exercise. Show that DDH implies CDH in source group. Good. Okay. So this part here, I already kind of jumped ahead a bit on. Can we still rely on the DDH assumption by linear groups? Is it still safe to use El-Gamal encryption in the source group G? And the answer is no. See discussion above. Discussion above. Right. However, we typically can still make the DDH is typically still safe to make DDH assumption in the target group. By the way, now let's go one step further. I'm saying that if we make the BDH assumption in the source group, then the DDH assumption has to hold in the target group. Can someone tell me why this is the case? No, what? No, let's make this an exercise. I mean, exercise. Show that DDH in target group follows from BDH. Okay, cool. Good. I would say at this point, let's do a 5 minute break because after the 5 minutes, it's exactly 11. So let's get back in 5 minutes. After these 5 minutes, we're gonna go to the next topic. Good. Hey.
Gibt es schon einen Termin für die Endklausur?
Oh. Da hatte ich genau noch nicht, da war ich mit der Frau Kraska,
Okay.
aber gut. Nee, also ich werde da gucken, dass es nicht, also ich habe den Kollisionskalender, dass es nicht mit irgendwas.
Ja, ich würde halt ganz gerne einfach einen Urlaub buchen. Dann,
okay, gut. Nee, dann mache ich das, weißt du was, da gehe ich dann nachher kurz bei ihr vorbei und mache das dann gleich aus.
Perfekt.
Alles klar, sorry für die Verzögerung.
Alles gut.
Ja.
Das überlege ich mir noch zweimal.
All right, is everyone back? Then let's let's continue. So I want to maybe looking ahead for the next topic. When we look at Jou's three-party key exchange, A, B, and C, one thing that happens here, right? We said A sends something like G to the A, B something like G to the C, and C sends something like G to the C. Then somehow, even though we're having three parties, we can just take any pair of two parties, right? Let's take these two. And form a virtual party. Virtual party AB. And now, of course, we could say the secret here is either A comma G to the B or B comma G to the A, but the public message, let's put it here, public message is E G to the A comma G to the B, right? E, which is EGG to the AB. And now, from the view of this party, C, right? He's essentially just doing a two-party key exchange with this virtual party AB, right? Because he sends to this party AB that it's in reality two parties. Doesn't have to matter for him because A and B get the same message from him. It's always G to the C. Sends his message G to the C to this virtual party. And somehow this virtual party, and of course they send him back G to the A and G to the B. And but we could think of it, this party is sending back E G to the A comma G to the B. Right? Now, of course, he does that pairing operation himself, but we could think of it as outsourced, right? And now he just needs his secret C to take this EGG to the AB, raise it to the C, and get the secret key, right? So this is sort of what the three-party key exchange allows us. It's to sort of bundle or pair up two parties together and treat them like a virtual party, right? Like a virtual joint party. Good. And this observation sort of is the segue to our next topic, a notion called identity-based encryption, right? So far, we've essentially seen encryptions in its private and public key flavor, but the most, let's say the ways we differentiated different public key encryption schemes was by the level of security that they achieve. It's basic, but the standard basic security notion for public key encryption is int CPA security, right? The adversary just sees keys, gets to select two challenge messages, and then sees the challenge ciphertext. CCA1, where the adversary gets an additional resource a decryption oracle in before choosing his messages, and CCA2, where he has a decryption oracle all along, right? So the different flavors that we've seen so far about public key encryption were mostly about different flavors of security, but not different flavors of functionality. It was always, syntactically, it was always the same. It was just a public key encryption scheme with a keygen, enc, and dec mechanism, right? But something that didn't give us any more flexibility. So, and now we're at this concept of identity-based encryption. So in standard public key encryption, before you can send a message, an encrypted message to me, I somehow need to make my public key available to you. I typically locally generate my public key and then put it, say, on my homepage, or put it like as an attachment into an email to you, whatever, right? There has to be a way that I convey my public key to you. Otherwise, we cannot communicate in an encrypted way, right? So one party sort of has to get their secret key to the other party. It doesn't really matter if we're in this interactive or non-interactive scenario. You have to get some information of me first before you can send me encrypted messages, right? Because we don't want to just exchange keys. We want to exchange messages. So in practice, this is done with something like something called a public key infrastructure, right? So typically, homepages, whenever you know the green padlock item when you browse in the web, that means your communication to this website is encrypted. Right, and how do you get these the key from this homepage in order to communicate with the server in an encrypted manner? Well, typically the server sends you this key, but how can you make sure it's the correct key? Well, the server has to obtain a signature from somewhere. Right, or what we're going to do is we're going to make sure that that the server really is who he pretends to be, and for that we're going to have an authority, a certificate of authority, which provides signatures of the server's key. Right, you have your own key, but to prove to me that this actually is that this is the key of this homepage that you claim that you are, the certificate authority will sign your key. As a matter of fact, what they're going to do is they're going to sign your signature key, and with your signature key, you can now sign keys. You can now sign your communication. So this is really mostly about signatures, right? But for that, we need to have some form of root trust. We need this signature authority that provides certificates, right? And when like so-called root signature keys get stolen, then something really bad happens. Then basically the security of large parts of the internet is going to be compromised, right? So this is how these things work in practice, but this is not the lecture in which I'm going to tell you how this is actually implemented in the real world. But high-level bit, trust in the internet, integrity is rooted in signatures, right? In there being some trusted bodies, trusted authorities that sign things for others. This is and the totality of this, or the entirety of this, we typically call a public key infrastructure. Right? You can think of this as a theorist. We always make things easier than they are in practice, so that we can really think about it in a simple way. We just model this as a public key infrastructure. Think of this as a gigantic bulletin board where everyone can write their key. And if I write my key onto this bulletin board, then it's trusted and it's associated with my identity, right? My identity being maybe my IP address or whatever address you want to associate to me, then this is trusted, right? We assume this public key infrastructure is trusted, right? And again, in theory land, where everything is simple, there's no chains of certificates and signatures. This is really just a giant public lookup table which associates each identity, let's say IP address, with the user's corresponding public key. Right, so if you have an IP address, there's an empty spot for you on this public key infrastructure at which only you can write your public key. Good. This is how it's currently done. However, if we want to do it like that, it makes it necessary that if I'm a sender, right, I'm someone who wants to talk to a website. So either I have to locally store the entire public key infrastructure table. This is a huge thing, like the public keys of everyone in the internet, or before I talk to someone, first retrieve their public key by talking to someone else, right? That means additional interaction. So before I can talk to any one of you securely, I first have to talk with a server to retrieve your public key, right? This sometimes creates a problem, right? Specifically, think of the following scenario. I'm not a person, but a sensor, somewhere in a network which has patchy internet access, but this sensor now decides that he needs to send a encrypted message to someone, but again, the connection is spotty. He knows this message will eventually be delivered, but not immediately, right? And in particular, there might be too much of a delay to retrieve the public key of this receiver, right? There might be network lag or whatever. You might be on a satellite where you're not having a line of sight connection. Think of some scenario, right? I mean, probably you can come up with better scenarios where you have a sensor which has only spotty access to a network, but who would like to send encrypted messages to a potentially large amount of receivers, right? And if you've ever worked with an Arduino, well, the base model has like 64 kilobytes of memory, not too much memory to store a lot of ciphertexts or keys for that matter, right? So public key encryption is great, but the drawback is you need to know the public key of every potential receiver, unless you're willing to invest additional interaction with someone. Is this clear? I mean, great. And this is precisely where identity-based encryption tries to make our life easier. So identity-based encryption, you can think of this as a modest attempt to overcome the need for public key infrastructures or the need to store large amounts of keys, right? So in a standard public key encryption scheme, everyone has their own public key. In identity-based encryption, there's just one public key for everyone. We call this a master public key. So you might say, okay, there's just a single public key and this public key is short. Wait a second. So how can I make sure that only the person who I want to talk to can decrypt and not everyone else, right? If everyone else has the same public key, then how can we make sure that the person I want to talk to can decrypt and someone else I'm currently not talking to cannot decrypt? Well, when we encrypt, we now need to take the receiver's identity into account. Right, so the sender, when he encrypts, he will know the master public key and a user-specific identity. This could be something like a name, an email address, an IP address, or a directory name in a file system. Right, we're not even necessarily talking about communication in space. This could also be about communication in time. When I store something in a file system, the address of this, or just the path of this directory could be the identity of the thing that I'm encrypting to. So generally, this is just a string, right? Think of it in easiest terms just as a binary string. So an identity is just a binary string, which, however, uniquely identifies the receiver. There's nothing secret about it, right? The string can be anything. There's no secret corresponding to this string. It only, again, I mean, when I send something to your address, you are the one who's going to receive it and not someone else. Something that uniquely identifies you, but that doesn't come with any secret, right? That's an identity. Good. So the senders will take this master public key and the identity to produce a ciphertext. And now, how do you decrypt? Well, in order to decrypt, you will have to have an identity-specific secret keys. So identity keys or user secret keys, they are generated by a key authority who holds the master secret key. So we have a key authority that publishes the master public key and keeps the master secret key for itself. Right? And now I can go to this authority and say, hey, I'm Nico Döttling. Please issue me a user secret key corresponding to this master public key for my identity. And the key authority can now generate a user secret key, which will allow me to decrypt all messages which are directed to me or where the encryptor used my identity. So a bit more formally, in identity-based encryption, we have a setup algorithm. It's sort of what used to be the keygen algorithm in public key encryption, but we have another algorithm here that's called keygen, so we have to give this another name. Sometimes it's called master keygen, but these days it's typically called the setup algorithm, right? This is run by a key authority. It just generates a master public key and a master secret key, right? And those are, think of them just like public and secret key in a public key encryption scheme. What's new now, the new functionality of IDE is actually what we call keygen here, which now has a different syntax. So keygen takes the master secret key and an identity and produces a user secret key skit. The encryption algorithm takes as input a master public key, an identity, a message M, and outputs a ciphertext C. And now decryption uses the identity secret key to decrypt a ciphertext. So I usually like to kind of draw it this way. Let's say Alice wants to talk to Bob. We have here the authority, right? Generate master public key, master secret, master secret key from setup, and master public key is sort of written in the sky. Everyone can see it. And now Alice, given this master a public key and let's say the identity of Bob, can produce a ciphertext C encrypting to MPK it Bob some message. C goes over here. Let's say Bob was lazy. He forgot to go to the authority and sort of register his identity to get a Bob-specific secret key. Bob is a lot like me, right? Sort of having hundreds of requests to do something, and then only when things are starting to get critical, he's like, okay, I should take care of this task now. Identity-based encryption, this is not an issue, right? Because he can just go now to the authority, center his identity, and get it Bob, and get back SK it Bob. Right? And now with this key, he can decrypt SK it D. He can decrypt this ciphertext M. So even if you were lazy, right, if you forgot to register your identity and people already started sending you encrypted messages, it is not an issue, because these algorithms here, you don't say that you have to do the key gen before the enc, right? The enc just takes the master public key, and the master public key does not change when I generate a key. It's always staying the same, right? So it doesn't matter if a ciphertext was encrypted before I got my user secret key or after I got my user secret key. This notion doesn't bother with that. It doesn't care about that, right? The functionality remains the same. And in terms of correctness, right? So we're jumping here already for security. Correctness is exactly this, right? Let's say we're asking, whoops. We're asking for all all messages. It holds that if we generate MPK, MSK setup, generate SK id, keygen, MSK it, and encrypt C as enc MPK. Ugh, okay, that's too narrow. Can I zoom in? Yes. Oh no. Here C is enc MPK it message M. If this is the case, then if I decrypt with SK id the ciphertext C, then this is M, right? This is perfect correctness. So we can, of course, relax. Yes, question. We can, of course, relax this to statistical correctness, where we just ask that the probability, right? That we ask for all identities and messages M, the probability that this holds be 1 minus negligible overall. Question.
So authority holds Bob's secret key.
Everyone's secret key. So the master secret key is short, right? But using this master, you can think it's a good way of thinking about it. The master secret key and here this no, why isn't it switching to this? Okay. Think master secret key is compressed representation of all secret keys of users in the system. Right, so both master public and master secret key are short. They're not, they're just strings of, let's say, 1024 bits or something, but there might be exponentially many users in the system. Right, and you can think of this master secret key as a compressed version of all secret keys in the system. Yes.
So technology can decrypt bombs.
Yes. That's why it needs to be trusted. So you've already found sort of the main concern that people have with this notion, why this notion, let's say, hasn't picked up in the way people thought it would, right? So if we think of users as real people, then you really need to trust the authority, not just a little, but a lot, right? Because the authority can basically decrypt encrypted messages directed to any user in the system. If the authority becomes dishonest, we have a problem, right? If every user, if every internet user in the world was to rely on one and the same master public key, and all of a sudden this master secret key gets corrupted or exfiltrated. This is the worst thing that could happen, right? This master secret key has to be stored somewhere, and you have to touch it because you have to generate new user secret keys, right? Every time a new user joins the system, you have to touch this master secret key in order to generate new user secret keys, right? But if somehow someone manages to break into the server that is run by the authority and kind of exfiltrate this master secret key, then there's a huge problem, right? This is the critical issue about identity-based encryption, right? Which is typically summarized or under the moniker key escrow problem. So when you read about that, then you know what's going on. However, this was how identity-based encryption sort of was first envisioned, right? But I personally think this motivation here, encrypted file systems, is much better, right? Because sort of there, let's say the universe, the users are programs on your computer, and the key holder, the key authority, that is you, right? So you can give programs running on your computer access rights to decrypt certain directories. You can give them user secret keys for certain directories, but nothing else, right? So when you think of users as algorithms and the key authority as yourself, this notion makes a lot more sense, right? Because now the worst thing that can happen is that a program somehow reads more on your computer than it should, right? But then how do you fix it? Well, you need to set up your computer again. You generate new keys and re-encrypt everything, right? So encrypted file systems is actually a very meaningful use of this notion of identity-based encryption. And you can also craft other use cases, but the idea that every user every internet user relies on the same key authority to keep the master secret key a secret is a bit wild, right? And that's why this notion of identity-based encryption, you might not have heard of this before or hear about this notion today for the first time. Now, of course, this has regained popularity with the rise of cryptocurrencies, because now you can you can use this functionality that IBE gives you in an interesting way. But yeah, the original intention is not a great one. Okay, I mean, we're doing a theory course here, right? Where we're studying what this notion gives you, or what you can do with it, right? We're looking at this from a somewhat neutral angle. Good. So now let's talk about security of identity-based encryption. And as you can expect, there are not a ton, but several different notions of security for IBE. So the de facto standard security notion for IBE is called full security. That's sort of typically the strongest security notion that we're asking for. And as usual, we define this via a security experiment, right? Of course, somewhat analogous to in CCA security. All right, so how does the experiment work? Now, again, A is a PPT adversary. He's against an encryption scheme. So his goal is to distinguish whether a ciphertext encrypts M0 or M1. Well, that's so far so expected. Good, but the experiment proceeds as follows. First, it generates master public and master secret key. And now it runs the adversary, and the adversary gets access to a key generation oracle, right? This key generation oracle, he can query it with identities, and he will get the corresponding user secret keys with respect to this master public key. Of course, adversary also gets the master public key. So he plays around with this key generation oracle for a while, right? He makes any poly number of queries, and then he says, okay, I want to attack this identity its star, and I please would like to get an encryption of either M0 or M1. These are two messages of his choice, right? Now, the important thing is he's only allowed to continue playing if the adversary has not queried the key generation oracle on the identity its star. If so, he could trivially win the game. He knows SK it, and then SK it star, and then distinguishing encryptions of M0 under its star versus encryptions of M1 under its star is trivial, right? He just decrypts. So he's only allowed to continue playing this game if he has not tried to cheat, right? And if this is the case, we proceed as usual in these kinds of experiments. We flip a random coin. If the coin is 0, we encrypt M0 with MTK and under its star. If the coin is 1, we encrypt M1. Now we give the adversary this ciphertext C star, and again the public key, and we could have passed the state between these two phases of the adversary, but here it doesn't make a difference. He can just, for instance, make the same queries that he made before. But in general, you can think this adversary of being stateful. Right? think of A as stateful. Good. Okay. Yeah, the adversary gets this information. Oh, PK. It should be MPK. Oh my. This is MPK. Good. Adversary gets again this stuff and the challenge ciphertext, and again access to a key generation oracle. However, this time he's explicitly not allowed to query the identity it star. Right? Before he could ask any identity, and he would just lose if afterwards if he chooses the challenge identity to be an identity which he queried earlier to the oracle. Now we explicitly forbid him to ask this identity. This is similar as in the CCA2 experiment, right, where we don't allow the adversary to query the decryption oracle with the challenge ciphertext. Here, the key gen oracle cannot be queried with the challenge identity. Adversary outputs a guess B prime, and he wins if B prime equals B. Otherwise, he loses. And as you might expect, we define the advantage. I think we're almost through. We define the advantage of such an adversary as his winning probability minus 1/2, absolute value of that, right? 1/2 we can always achieve by blindly guessing, right? And you can always achieve winning probability 1/2. So we again just measure how much better our adversary is 1/2, better than 1/2. And we say that an IDE scheme is fully secure if every PPT adversary only has negligible advantage. Right, sort of the expected notion, and in a way, this is the strongest notion. When we're looking at weaker notions, right, we can say the adversary sort of only gets access to the key generation oracle in the first phase, or a seemingly very weak notion, the adversary has to announce its star before getting access to any of the oracles, right? There, this is called selective security. This is very non-adaptive. So there, even before seeing the key, he has to decide what his challenge identity is, right? For a very long time, it was actually thought that these are really different notions. I mean, you can easily build a scheme which is selectively secure but not fully secure. Make this as an exercise. But the question of whether when you have a selectively secure scheme, can you kind of always build a fully secure scheme from it? That was open for many years. As a matter of fact, it was myself and a collaborator who solved this back in 2017. Right, that any maximally weak secure identity-based encryption scheme gives you one that has the strongest notion of security. Right, so there is a way of really strongly amplifying the security from extremely weak to maximally strong without making new assumptions. Right, but that stuff. Let's say uses, let's say too much machinery for this course. We keep it here for now. I think we're almost through. Let me quickly, because that's going to make my life then in the next lecture easier. Say we can for identity-based encryption, we can define something we call a key encapsulation mechanism, where when we encrypt to a user, did I provide the syntax? No, then, okay, before going into that, I will quickly provide the syntax for IB chems. So there, the encryption algorithm doesn't take a message as an input, but just master public key and identity, and produces a gives me a key that I can then use for hybrid encryption. But okay, since the syntax is, why did I not have the syntax here? Good. Then let's do this next time. Our time is anyway over. And please, if you are, if you cannot attend the quiz next week, please quickly come here so I can take note. One more question.
Yeah. What for quiz? Like, can we get some?
It's one page of yes/no questions, essentially. I mean, look, it's just a minimal barrier to make sure that you were actually here in this course, right? Working in this and for this course, and you're not just someone who, again, this happens a lot, right? Who thinks like, I still need to get some credit points somewhere. What course is there? And then sign yourself in before the exam, right? This is like the minimal entrance barrier I'm asking of you, right? Because when you want to do the exam, I want you kind of to be here and interact, right? This is not just a ECTS point generator, but yeah, sorry, I have to say it like that. I mean, this is experience, right? But
Will there be another chance?
Yeah, of course, there's going to be a